Hi Ram, good morning. How are you?
Fine, sir.
And everything going good? Able to solve the questions, right?
Yes, sir.
And which I have uploaded on the Google Drive. That too you are doing, right?
Not done totally, sir, but I will complete by today, sir.
You have 1 week. Entire
Yes.
week you take this one. Till Sunday you can do.
Okay, sir.
He's joining. Just a minute. Good morning, Mrinal. And so let's start now. Okay, if possible, please turn on your videos as well. Okay, let's begin with the dual nature of electromagnetic radiation. I have a question for you guys. What is electromagnetic radiation? Can anyone of you answer this? What is an electromagnetic radiation?
It is particle and wave at the same time.
Okay, it's fine. No, that is you are talking about the dual nature of that electromagnetic radiation. I'm asking what is electromagnetic radiation?
Sir, alpha, beta, gamma rays, light rays
Okay. Basically, someone told that it's light rays. It's light.
with different wavelength.
Light with different wavelength. Okay. Okay. Let me tell you this. That what is electromagnetic radiation? A radiation which has electric field component. See here. I will draw something. Let us say my electric field is in this direction. Okay, represented by E. And there is another component called magnetic field component represented by B in the Z direction. If these two components are there and they are like this, see, listen carefully. They are like this. Electric field going like this, magnetic field going like this, or coming out or going inwards, backwards. This is like this. This is happening like this. Okay, this is happening like this. Then what happens? Whatever the energy you have, it will be going in this direction. Your electric field is like this, magnetic field is like this, and if these two things are there in any case, in any charged particle, electric field and magnetic field will definitely arise. Repeating again, in any charged particle, electric field and magnetic field will definitely arise. If magnetic field is moving like this, electric field is moving like this, or in opposite way also. So the propagation where your light travels, where that particle, where that energy will travel, it will be perpendicular to both of the fields, electric field as well and magnetic field as well. That means if electric field is moving like this, magnetic field is moving like this, then your propagation of light will be in this direction. Propagation of light. That means, sir, it means whatever the energy or whatever the light you can see coming from the sun, right? You can see that because it's the propagation of light in the direction of Earth. The electric field vector and the magnetic field vector will be perpendicular to that propagation of light. That is why only you are able to see that light. I hope this is clear to you. Okay. And this propagation of light, the propagation of electromagnetic radiation occurs in the wave nature. It occurs in the form of the wave nature. See, can you think that a particle can travel in vacuum and reach to Earth? See, we know that in space there is all vacuum, right? There is vacuum. It's no air present there, right? In vacuum, can a particle of light travel to Earth? And can you get that sunlight here? No, it's not possible. It's not at all possible. What happens is my light is traveling in a wave nature if it is coming from sun like this. See, this is the direction of propagation of light. In this manner, wave is coming. Okay, it's fine. This is okay, right?
Yes, sir.
Okay. So that means I mean to say that okay, we now know that okay, if a light can reach up to the earth, if a sunlight can reach up to the earth, that means it is following the wave nature. Okay, wave nature is we got to know that okay, it is following the wave nature. So what is a wave? What is a wave? A normal wave I am asking. What is a normal wave? A normal wave is like this. Okay. Okay. Now, if I ask you, what is this called? This is called as a crest, and this is called as a trough. Okay. From the straight line, from the axis, from the origin, this distance or this distance is called as amplitude, and the distance between two crests or two troughs is called as your wavelength. This is what my wavelength is. Okay. Okay. Then, okay. Then if I ask you, can you tell me if I draw a wave like this and I draw a wave like this, whose lambda is bigger? First, whose lambda is more? Whose lambda is higher? Can you
Second
tell
one.
this?
Second one.
Second one. Second one lambda is higher. Okay, very good. Now there is another term which is called frequency. You might have heard it, right? Frequency. What does frequency means? That how many cycles? Frequency says that, okay, in 1 second, frequency is represented by nu, says that in 1 second, how many cycles can be passed? Cycles of what? Cycles of these waves can be passed. Okay, let's say if I am fixing the time as 1 second, so this is traveling in 1 second, 2 cycles. Let's say this is 2 cycles, right? From here, this is one cycle. See, from here it is one cycle. From here it is 2 cycles, right? These are the 2 cycles. So in 1 second, I can say maybe only 2 seconds are passed. But if you see this one, maybe in 1 second, more number of cycles can be passed. Are you agreeing with me? Yeah. So frequency depends in 1 second how much distance is you are able to cover. How much distance you are able to cover. Okay. So if I ask you now, let's say I am giving you a fixed time. Okay, that my wave is traveling up to here, just here. Okay. And in the other case, I am saying that I am starting from the same region, but I am drawing something like this. And I am ending at the same point where this wave ends. So now, both waves has gone for the same time. So in which case, the frequency is more. In which case, the frequency is more. Can you tell? Both have traveled with the same time.
Second one.
Both have gone to the same distance. Yes. In the second one, my number of cycles are how many? Let's find it out. 1, 2, 3, 4, 5, 6, 7 cycles. And here, it's just one cycle from here and 2 cycles only, I can say. Just 2 cycles it has formed. I hope this is clear. Yeah. So that is why the frequency of this region is higher. And frequency, okay, let me clear this. Lambda is represented in meters. Frequency is represented in terms of second inverse. These are the units, first of all. Remember? Okay. So now, because I can see that I can have multiple frequencies, I can have multiple wavelengths as well, right? So due to that, we can define or we can create a overall electromagnetic radiation. Like whatever type of radiation I can get in the entire universe, I'm arranging them in some particular ranges. Okay, ranges of frequencies or ranges of wavelengths. Let's say if your frequency is too large or if your wavelength is too small, so I can show in this manner, maybe very, very, very small in this manner. After that, maybe little bit distance will be increased, wavelength will be increasing, maybe it will be more increasing, maybe it will be more increasing now, and it will be like increasing nature, it will be going on. Are you getting this? Okay, so what you can do is, you can define few particular regions. The region with the minimum wavelength, because this is a region of minimum wavelength, this is called gamma rays region. Gamma rays. There is another one which is having even more small wavelength, which is cosmic rays, but we are not going into that. Gamma rays. Then comes this is as X-rays. We have X-rays over here. Then comes your UV and visible region. UV visible. First UV will come, then visible will come. Okay, visible means this is the visible light which you can see. Visible light which we can see. So what do we mean by visible light? Um, Maybe what? See, I am writing with a blue color, right? So this blue color you can see, that is your visible light. I hope this is clear. Then after that, comes your IR rays, infrared rays. Then comes this part. This is microwave. And then in the last, this one, which is radio waves, having the maximum wavelength. So question is that which particular electromagnetic radiation has the maximum wavelength? Radio waves. Minimum wavelength, gamma rays, or if the option is cosmic rays is given, then mark cosmic rays as well. Okay. I hope this is clear. This is a region of electromagnetic radiation. We do not need, no need to remember what is the at what wavelength we are getting these values. Okay. Just remember one thing, that the radio waves can range from a millimeter range to a meter range. This radio waves ranges from millimeter range to meter range. Just remember this thing. I don't think so anything else is required here. Okay. Then comes the next thing. Now, up till now, we now know everything about a wave. That how a wave propagates, what like how a wave forms. Wave forms due to the simultaneous movement of electric field vector and the magnetic field vector. That is how a wave forms. And wave can travel in the vacuum also. Acha, what is the speed of a wave? Do you know this? At what speed this wave travels? In vacuum also maybe. So write few characteristic about a wave. Okay, travels at 3 into 10 to the power 8 meter per second speed or velocity, which is nothing but speed of light. How we define speed of light? The speed of propagation of the wave of light. This is the speed of light. Okay, this is the first thing. Second thing is that they do not require any medium. Do not require any medium of propagation. Propagation. Okay, and it can have it can have variety of wavelengths and frequencies in the whole region. Okay, these are the few characteristics of this wave. Any wave in this world will follow these characteristics. I hope this is clear to you. Yeah. Now, one thing we understood that okay, from this and from our original point of view, from our own perspective also, we have now know that the sunlight which is coming to Earth or coming to any planet must be having the wave nature, because wave is the only thing which can travel in the vacuum. Particle can never travel in the vacuum. Particle needs some medium to travel. I hope this is 100% clear to you, right? Can I move further?
Yes, sir.
Okay, good then. Then comes the part. Okay, I will ask you one question. That okay, maybe if you have a metal block here. Okay, I'm taking a metal block here. If sunlight is coming, let's say in this manner, if sunlight is coming here, what happens if it collides with the metal block? What will happen? Any idea? Something will happen or nothing will happen? Any idea you have? No idea it means, right?
It will reflect.
It will reflect. Okay, sir. It will reflect. Okay, it will just collide, it will reflect, it will go back. I said, okay, this is fine. But this was not observed. The thing which you are saying to me, that was not observed actually. Now, okay, let me tell you one more thing also, that whatever the light we were talking about here, we now know the frequency of light as nu, right? So that particular light is carrying some energy which is proportional to its frequency only. Removing the proportionality constant, you will be getting a constant called Planck's constant, which is h, having a fixed value of 6.626 into 10 to the power minus 34 joule per meter per second. Okay, this is fine.
Yes, sir.
Oh, sorry, joule, not joule per meter per second, joule per second, joule second. Yeah, joule second. This is having this fixed value. Okay, sir, it's fine. So then I say, okay, if a wave is coming here and is colliding with the metal, this whatever the light you are having, this is coming with a energy which is equal to h nu. Of course, this wave will be having some frequency, and so that it will be having some energy as well. You guys thought that okay, it will be reflected, but it didn't get reflected. It reflects, but not as a whole. What was observed is that if this energy is high, how much high I will talk about later. If this energy is high, what it does, it ionizes the metal. Do you know what do you mean by ionization? Removal of electrons from a metal or from any substance. Removal of electron. What happens is the point, the place at the metal surface where this light has came, light has you can say has striked, from that particular point, electrons were ejected out. Now we were thinking, what? How this is possible? How a wave can give its energy to a particle? Because electron is a particle, we know that, right? We know that electron is a particle. Electron is not a wave. How a wave can transfer its energy to electron? It's not possible, right? Do you agree with me?
Yes, sir.
But then the electron was ejecting out, electron gets ejected out. So there was something we were missing, or there was some unusual thing which was happening, right? So what was this? This process, this whole process, the electron ejection process, due to the electromagnetic radiation, it was said as photoelectric effect. Photoelectric effect. Okay. Okay. So what happened is, what they saw is the same thing. Okay. Then they have interpreted something that if a metal gets ionized, when can a metal get ionized? When the electron is detached. Like if you want to detach the electron from a metal, you need to provide some energy to that electron so that it can be ejected out. If you give energy to the electron, it will get ejected out. But sir, how that energy will be given? If there is some particle which comes with an energy, I'm repeating again. If there is some particle which is coming with an energy and strikes the electron, like with that striking, electron will be go out. Let's say if someone is like this, standing here, okay? I am coming with my energy, okay? I just push this my hand. So my this hand is gone, right? In this manner, if it is collision is happening, my hand is also moving, so that electron will also move with some particle. See, this hand is my particle, right? It's not a wave. If my particle is striking it, colliding with it, this hand is moving. Similarly, if your any particle comes and electron is sitting over here peacefully, if it comes and if it strikes this, electron will get more energy now. It can be moved. It can be ejected out. That is the thing. So that means, sir, you require a particle here. You mean that means that we require a particle here, not we do not require here the wave. We require the particle here. That means, sir, the like if the electron is getting ejected out, your light is behaving as particle. Yes, of course, it is. It is behaving as a particle. So, sir, this experiments that means it proves that what is how the light behaves as a particle. Yes, exactly. This is what this experiments tell you. Confirmation of particle nature of light. Okay, now I will give you the whole explanation of the photoelectric effect as well, that what happened and how it happened. Okay, so see, let's discuss this even more further. So the proper thing this way, that I am having a metal plate whose surface I am drawing, the upper layer, which you can touch. Surface is the thing which you can touch. If I can touch my hand here, this is my hand surface. Okay, inside my hand there are many blood cells, blood vessels, whatever, I don't know. Biology I also don't know. But whatever the things are there, right? This is the surface only I am able to touch of my hand. Okay, bones are there, whatever. Okay. So on this bowl, I am striking with some light, and now this light is having the particle nature. That means light is coming in the form of particles. And these particles of light is called as quanta. What do you say as? Quanta of particles. That means combination of particles like this. This is my one quanta of particle. It can be my other quanta of particle like this. This is called a quanta. Packets. Light is coming in the form of packets of energy. Light is coming in the form of packets of energy, which is called as quanta. So whenever my light hits it, if there can be two possibilities now, electron may or may not be ejected out. So, sir, when it will be ejected out, that is the thing for us to know when it will be ejected out. So, see, can you see? Okay, let me explain you one thing. If there is a nucleus in between and the electrons are here surrounding this nucleus, you know na, how atom looks like. This is how an atom looks like normally, right? A positive charge nucleus is there, electron is there, electron is there, like this. Okay. And because positive and negative attracts with each other, this electron must be attracted with this nucleus. Now, if that energy which you are bringing from the light is sufficient enough to break this attractive force between the positive charge and the electron, this electron will be ejected out. This is the thing. This much energy is minimum required for an electron to be ejected out. If your particles is bringing this much energy, then this electron can be ejected out. I hope this is 100% clear to you. Yeah. So then, that is why I have written may or may not. Maybe the particles are coming with this much energy. Maybe the particles are not coming with this much energy. Okay. So that is how we will define it. So let us call the energy to just remove the electron is nu naught, or the frequency at which, because we know that energy and frequency are directly linked, right? So I can say that the frequency of light which was required to break this attractive force between the nucleus and the electron was nu naught. So corresponding energy will be E naught, can I say? Where E naught is my h nu naught. And this energy is called as threshold energy. Threshold energy. And this frequency is called as threshold frequency. Is it okay for you guys? Please unmute yourself and tell me.
Yes,
This
sir.
one here. Mrinal, you also? It's fine?
Yes, sir.
Okay, very good. Okay. So now there can be two cases. Case number one. The packets of light the packets of light which are coming has a frequency of nu. Let us say that has a frequency of nu, so the energy will be E. Correspondingly, I'm saying the energy will be E, which is h nu. Okay, whatever the packet of light energy bringing their energy with them. Okay, because we know now that the light can have multiple energies as well. Okay, because light have multiple frequencies, so light can have multiple energies according to the whole spectrum I showed: gamma rays, X rays, whatever, all of them having some different energies. Okay, now listen to me carefully here. Case number one I am taking. If your let's say if your nu is less than nu naught, or my E is less than my E naught, what will happen? Will your electron be ejected out or no? Can you tell me this answer? E naught was the minimum energy which was required to remove an electron out. Am I giving that much energy to the metal surface? No, I don't have. My light particles do not have that much energy. It is smaller than E naught. So will the electrons be coming out? Of course not. Do you agree? Yeah? Is this fine?
Yes, sir.
Okay, can I say then no electrons will be coming, no electrons will come out? Yes, no electrons will come out. This is the first case. Okay. Then let us take case 2. Case 2 is, let's say my E and E naught becomes equal. That means your nu and nu naught becomes equal. Yes, what will happen? Will your electron be ejected out? Of course, electron will be ejected out. Electrons gets ejected out from the metal surface. Case number 3 we will take where my nu is greater than nu naught. So of course I am taking that means E is greater than E naught. So then in this case what will happen? Sir, if your incoming particle energy is higher than the energy of the electron and a incoming particle, let's say see here, see one thing, see here. If I am striking my hand with some energy which is very less, this will not move. That means electrons is not coming out. If let's say I am moving, if I am hitting with some more energy, maybe in with this energy some electrons are getting out. Let's say that this is electron. Okay, let's say this is electron. If I'm hitting it with this small energy, nothing happens, this is not moving at all. If I am hitting with some more energy, okay, this will start, this will just see it is this is the fixed position of the electron. Okay, this is the fixed position of the electron. I am hitting with some lower energy, nothing happens, it stays here. That means it doesn't get ejected out. If you are hitting some with some more energy, it just shifts here. That means it ejects out, but it is not moving, it is still the same. Now if you are hitting with some very high energy like this, it starts moving. It will start moving because it will get more energy now, na? It gets more kinetic. You can say that energy which the light has hit has also been used to like for the electron to get its movement, for electrons to get its momentum. Think this way. Okay, so that is how it defines. If your nu and nu no, nu is greater than nu naught and E is greater than E naught, then of course some of the energy, some part of the energy I can say will be, some part of this energy I am saying is will be used for the electron to be ejected out, which is equal to E naught, right? And the rest of the energy will be used or will be converted in the form of kinetic energy of the electron because the electron starts moving. Is it okay? Is it 100% okay?
Yes,
Yeah.
sir.
Okay. That means, sir, if this is the scenario, can I calculate the kinetic energy of electron? Of course, why not? You can calculate the kinetic energy of electron very easily. How, sir? Kinetic energy is nothing but, see, I was having the total energy as E, and the energy which was required to just eject the electron out was E naught. So if I am doing E minus E naught, whatever the remaining energy I will be having, it will be converted to kinetic energy for electron. Yes, of course. This will be. This is true. And similarly, I can write it as this manner also, that Ke is equal to h nu minus h nu naught. Yes, these two things must be clear to you. Very important. This is very important. This thing. Is it okay? 100% clear? Please tell me this if this is
Yes,
clear or
sir.
not.
Clear.
Mridal, you also? It's fine?
Yes, sir. Yes, sir.
Okay, good then. So then there were more observations taken because now we are at a stage where we can where we know that when can electron be ejected out, when it cannot be ejected out. Let's say once the electron gets ejected out, we are thinking of some more thing. Okay. Acha, tell me, is electron a charged particle? Is electron a charged particle? Yes, of course. So the movement of charged particle will give you a current or not? Will it give you some current or not? Tell me. Will it gives you some current or not? Do you know that moving charge particles generates current? This is the thing. Moving charge particles generate currents as well and generates magnetic field as well. Both they do. They create magnetic field and they also create current. Okay. So if I ask, okay, if let's say if more number of particles are or more number of electrons are getting ejected out, so will my current be also increasing? Yes, that means I can plot a graph of photoelectric current, photoelectric current versus your, let's say, frequency, versus your frequency. So now think a little bit. Let's say I am at this frequency. I am not saying that this frequency is enough to even remove an electron from the metal surface. So will any current be coming here? Will any current be coming from here? Of course not, right? Current will not be coming here. Do you agree with me? Yeah? Till the time your electron is not getting ejected out, no current will start to flow. Because if electron is not there, if any charge particle is not moving, the current will not become. I hope this is clear. Now, but let's say this at this frequency, this is my nu naught frequency. At this, electron will be getting ejected out, of course. So, can I say after this, if electron gets ejected out and if I increase the frequency, my kinetic energy of electron will also increase. So, can I say the photoelectric current will rise? Because the frequency is also rising, the kinetic energy will be rising. If the electron is moving with the more kinetic energy, it will be having the more current. Do you agree with me? Yes?
Yes, sir.
Is it correct or is it wrong? Will the frequency and current, will they depend on each other? Any of your thoughts? Will the speed of the moving electron and the current will depend on each other? See, I am asking you the two cases. One is the speed of the electron will increase the current, or the second thing is that will the number of electrons, if they are increased, they will increase. They will, what I can say, they will increase the current. What is
Number
correct?
of second one is correct.
Second one is correct. That if the number of electrons are more, then the current will be more. There is no relation of current with the speed. That means, sir, whatever you have drawn is wrong, and they will definitely give you this in an option. That the photoelectric current is linearly dependent with the frequency, and this is wrong. No, it never. It is never. Okay, we know that moving charge particles generate current, but it's fine. But the if the speed of that particle, if the speed of an electron is more, it is having no relation at all with our photoelectric current. Okay, then sir, how will the plot looks like? How will this plot look like? It looks like this. If a photoelectric current you are drawing here, taking this side, and here I am taking the new value, and let's say this is my new naught. So suddenly what will happen? Suddenly if the electron starts to eject out, so from here itself, the photoelectron, the photoelectric current is being constant because if you increase the frequency as well, electron will be removing at a normal pace. There will be like, if you increase the frequency, the kinetic energy of electron will increase. Listen to me carefully. If you increase the frequency, the kinetic energy of electrons will increase. But I am never saying that the number of electrons getting ejected out will increase. No, not at all. The number of electrons getting ejected out from the metal will never increase with the frequency. Only the kinetic energy of that electron will increase. See, this is a plot of photoelectric current versus nu. Photoelectric current depends on number of electrons itself. So if changing the frequency is not uh, giving me more electrons, so of course the photoelectric current will remain constant at all frequencies after nu naught, because after nu naught only the electrons will start coming out. I hope this is 100% clear to you. Yeah. So sir, if I plot here another plot, which is, wait, if we plot here another graph, which is kinetic energy of electron versus frequency, then what is your thought? Then what is your thought? Can I know it? Then will there be kinetic energy from the beginning with the electron? No, not at all. After the nu naught value itself, I'll be getting some kinetic energy. Yes, and that kinetic energy will definitely increase with the increase in the new value. Do you agree with me? Yes. The extra energy is there, na? That will be given to electrons so that the energy of the electron, the kinetic energy of the electron will be increased. This is true. This is 100% true. Yes, this plot will look like this. Then, sir, one thing is there. If I want to increase the photoelectric current, how can I do that? That means you have to increase the number of electrons only? Yes, of course, we have to increase the number of electrons only. Like, how can we increase the number of electrons? That is my concern. To increase the number of electrons, you need to increase the intensity of light. We need to increase the intensity of light. This is the light at high intensity zone. And this is at low intensity zone. Now, can anyone tell me what do we mean by intensity in simpler terms, in layman language maybe? Can anyone tell me this?
Sir, like more frequency.
No frequency. If frequency is, I am increasing the frequency here. But more frequency is not giving me the more number of electrons, right? Intensity is something different then. Intensity simply means the brightness. The brightness of light. If you are putting more brighter light onto the metal surface, more number of electrons will be ejected out. If you are putting less brightness onto the metal surface, less number of electrons will be ejected out. Is it okay for you? Intensity in layman terms means brightness of light. If light is very, very bright, more electrons will be coming out. If light is very, very less bright, very less electrons will be coming out. I hope this is clear to you.
Yes, sir.
At the same nu naught value, I can get two types of photoelectric currents. One with a low intensity light, I will be getting the low photoelectric current. If the light is having more brightness or more high intensity, I will be getting the high photoelectric current because a more number of electrons will be getting ejected out. I hope this is 100% clear to you. So, sir, if we try to plot something like this, that kinetic energy versus intensity of light, what will happen then? Kinetic energy versus intensity of light. Will they be having any relation among each other? So kinetic energy only depends on frequency. If a frequency is increased, then only the kinetic energy will increase. Intensity does not have any relation with the intensity. Kinetic energy will remain constant with the increasing intensity. Is it 100% clear to you? Please tell this. It's fine.
Yes, sir.
Mrinal, you also it's fine?
Yes, sir.
Okay, one thing I will want to discuss here, that we know now E is equal to h nu, right? This we know. Now nu can be represented as c by lambda, where c is your speed of light, and lambda you know it's the wavelength. Okay, so I can write my E as hc by lambda as well, and this is all the Planck's quantum theory. This is your Planck's theory. So please note this down. You will be definitely getting one question either from this formula or from this formula. Remember here, lambda they will give you in nanometers in the paper. In the exams, lambda they will give you in the nanometers, okay? Given in the nanometer scale, but you have to convert it into meters. How can we convert nanometer to meters? It is 10 to the power minus 9 meters. Is it okay? This is how they will give you. So you have to calculate you have to calculate the energy value only, so you can do it. Okay, or energy will be given to you. They will ask you lambda in nanometers. They will ask you lambda. Remember that they will ask you in nanometers. Whatever the lambda you were getting initially will be in meters. Convert it into nanometers again. Okay. So this type of questions can be asked. And now we are at a stage where I can teach you another model. Acha, one thing I want to discuss here. Are you now clear with that the light has two different natures? One is a wave nature, which we can see that the sunlight is coming to Earth from that way, and the particle nature, which we can see from the photoelectric effect that okay, if the electron is getting ejected out, some particle is striking that electron so that it is moving. This is coming out. Yeah, so there are two types of nature of light. Please remember this in your mind for next class, till next class at least. Okay. Now the thing is, there's another model. We have discussed till the Rutherford model, right? And the Rutherford model has many problems also, and he never explained many things with us to us. So the new model which is there is Bohr model, and I want to tell you that Bohr was a student of Rutherford itself. Bohr was a student of Rutherford itself, but Bohr did a very nice research. Okay, do you remember that Maxwell scientist told to Rutherford that Rutherford, your theory is incorrect because if a moving charge particle is there and it is constantly moving, it will lose some radiation and the whole atom will be collapsed and the atom will be destroyed. That was a limitation because Rutherford said that electrons move in a circular path around the nucleus, which was totally wrong. Like, okay, electrons move in a circular path, that Bohr will also say, but Rutherford was unable to explain why is it so. Okay, because according to Maxwell, any moving charge particle, if it is constantly moving, it will release some energy at each and every point, and the atom will be collapsed. This was a limitation of Rutherford, which he was not able to explain. But Bohr explained this limitation. See how Bohr said that the electrons move in a circular path around the nucleus, around the nucleus in fixed orbits, in fixed orbits. Not at every point the electron will be there. Sir, what it means? Bohr said that, okay, if you are having nucleus over here, let's say your electron is here, moving here up to this radius. From here to here, this radius is there. Okay. But it will never be happen that the electron is here. No. There will be no electron in the blue region. Bohr said that, okay, it might possible that the electron is moving in the green region, but it never be possible that electron will be moving in a red region. No. Bohr said that there are some particular orbits in which electron can be moved. In which electron can be moved. So, sir, how we will be knowing which orbit electron will be there and which orbit electron will not be there? That is our question, right? How you will be saying that? So, to explain this part, Bohr has used something very cool, very interesting. Okay, in which classes you are currently? 11th class? Both of you? Yeah?
Yeah, I am 11th class only, sir.
Sorry?
I am 11th class only, sir.
Okay, Mrinal, you are also in 11th standard?
No, sir. Done with 12th.
Oh, so I want to ask you, Mrinal, if you have done physics also in your 11th class, do you know something about centripetal force? And maybe Ram, till now, this time you
Yes,
also
sir.
have know this.
Yes, sir.
Centripetal force, yeah? What is centripetal force and when it
Force
arrives?
pulling towards the center with more
Yeah, if
pressure.
any species is moving in like this circular motion, if any species is going a circular motion, there will be a force which is exerting outwards to that. Yeah,
V
right?
square by R.
That is centrifugal, no, sir. Outwards.
No, 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 no. Centripetal is the force which is acting on a particle when particle moves, and that force is outwards the particle. The centrifugal one is inwards. Are you getting
No,
this point or no?
centripetal is
Centrifugal is
inward.
inwards, like
Centrifugal is
towards the.
outward, sir. Centripetal is inward,
No,
inside.
it's not like that. You are saying it opposite. I, who taught you this? I don't know. Okay, but whatever. It's like that only. That
Towards the center is centripetal. Towards the outside is centrifugal.
okay. Which book you followed for this?
सर आप
Any?
गूगल में भी सर्च करें तो वही बोलते सर.
It's not like that. You can check the H.C. Verma's book. I hope you know who is that guy, physics.
Yes,
He's a
sir.
physics genius, right? He defined the centripetal force as when your electron is moving and the force is exerting outwards to it. That is the centripetal force we talk about usually. Okay. Maybe some books is giving. See, there are two. These two are the relative terms. One is centrifugal.
Both
For
have
me,
equal forces but
yes,
different
equal
meanings.
forces. So sometimes people, because they are relative terms, so people interchange also. I am not saying you are wrong. I am saying that is also fine. But okay, you can either define centrifugal force because you have written that way. I can also define it for you then in that manner. Okay. Now see one more thing here. But yeah, the exact definition of centripetal force is that outward electron moving outwards. Okay. Okay, leave it. The thing is, if this electron is moving in a circular motion, it will be definitely experiencing some, according to you, the centrifugal force, right? Which is equal to mv square by r. So, sir, definitely if this kind of situation is occurring, then electron will be getting out of the system of this nucleus and whatever the atom, if this kind of thing is happening. But it is not, right? Electron is constantly moving. So there is some force which is acting as a centripetal force according to you, which is pushing the electron inwards as well. Isn't it? Yes? So that force is nothing but your Coulombic force of interaction. The attraction force between the nucleus and this electron, any electron, is your centripetal force according to you, which is equal to k q1 q2 by r square. Is it okay for you? So this was the relation given by the Bohr. He said this way that these two forces, they are balanced with each other, and that is the reason that we are saying electron is not going anywhere. It is moving in a fixed orbit. And see, this distance is highly dependent on the r values. If you are taking any radius from the nucleus, electron, you might be not getting any electron there. There is a fixed radius at which you can get the electron, and that particular radius can be calculated from here, and with some other formula which says, Bohr also says, this is the first statement of Bohr which he says, and there is another statement of Bohr which he says that the angular momentum is integral multiple of h by 2 pi. That the angular momentum, do you know what is angular momentum? Any idea? What is angular momentum?
mr omega square. Yeah.
Okay, maybe in terms of linear if I ask then?
mv square by r.
No, that is not how mv square by r. Okay, tell me about linear momentum. I am just asking you linear momentum. What is momentum? How momentum looks like? mv?
Yes
And
sir,
if it's a
mv
linear
sir.
direction, can I say it is multiplied with the linear side r? Of course.
Yes.
MVR, he said that MVR will be the integral multiple of h by 2 pi. He said like this. And this is again coming from the Planck's theory. Okay, you will be understanding this later, or this is not the part of our AP syllabus, but yes, he said that it's an integral multiple. That means there are some fixed values of n which are integers, and from here also you can define the radius. That only at this particular integer values of n I'll be getting something. I'll be getting my electron. Okay, so you combining these two relations, he told that we can calculate the velocity of electron, we can calculate the radius of electron, and we can also calculate the total energy of electron, and the calculation of these are not in the part of our syllabus for the APs. I'm just giving you this formula. Is it okay for you? I hope this is clear.
Yes sir.
Okay, good then. So this was all about what Bohr said, but the problem is now, uh, in the Bohr model also there were many problems actually. Do you know that we now talked about now something that, okay, I just want to explain one more thing here. Let's say the case one we talked about where the frequency of light or the energy of light was lesser than the energy required to remove the electron. But that particular, let's say this is my electron at a fixed position, I am striking with some low energy. My particle is, I am striking my light particle with the electron with some less energy. Electron will not be moving. But this energy was transferred or not? Yes, this energy was given to the electron, right? Do you agree with me? This energy was not able to overcome the attraction force between the nucleus and electron. That is why electron was not able to eject out. But at least the light particle has given its energy to the electron, right? Of course, light has given its this electron its energy. Then where this energy is going? It is with the electron, right? It is present inside the electron now. That means the electron has increased its energy. Yes, electron has increased in its energy, and that what Bohr said as well, that if you want any electron to go to higher energy state, listen to me very carefully. If you want any electron to go to higher energy state, let's say my electron is present here, I want my this red electron to go to here, from here to here. I want my electron to go to here to here. How can I do that? So there must be an energy which is corresponding to the difference between these two orbits energy. If that energy, this, let's say this is called as delta E, the difference between the energy of the second orbit and the difference in the energy of the first orbit. That means it is nothing but E2 minus E1. Let me say like this. If this value, if this delta E matches with the incoming light energy, which is h nu, then your this electron can go here. I hope this is 100% clear to you. Yeah. If that energy gap between the two orbits matches with the energy of the light which is coming, then this particular electron can be sent over here. Maybe you want, we can send our electron to the third orbit as well, no issue. You can send your electron to this orbit as well. For that, let's say this is my third orbit, so it will be having some energy E3. If you want to do that, so this will be my total gap from first orbit to third orbit, yes. So let's say this is my delta E again, and this time delta E will be nothing but E3 minus E1. And this gap is larger, so I'm wanting more higher energy. So there is a fixed value of energy of light. If it is coming towards to the electron, that electron can absorb that energy and can just shift its orbit. It can go to higher orbits. Now I want to ask you, where is the electron more stable? In the lower orbits or in the higher orbits? Where is the electron more stable?
Lower orbits.
And the reason for that, maybe, if I ask, what is the reason for that? Why is the electron more stable in the lower orbits? Any idea? Because because the electron present in the lower orbit is more strongly attracted by the nucleus, and there is more force of attraction between a positively charged and a negatively charged species, which releases energy, due to which this electron is more stable. That is the thing. Okay, if you're going very far from the nucleus, the attraction force from the nucleus to the electron will decrease, and due to which that electron maybe, it's like, if the attraction is less, then that particular thing is not stable. In chemistry, this always happens. Whenever the attraction force is higher, the thing becomes more stable. Just think this way. I don't want to go in details for now. Okay. Okay, this is one thing. Second thing, now what was observed is that, if you now understood na one thing, that if my h nu delta E was equal to the incoming energy of, like, incoming light energy, then this electron can be jumped. It is possible to jump the orbits of the electron. Yes, I totally agree with this, and you also will agree with me. So this is correct. Then what happened is that, okay, let's say that, do you know what is a white light? It is a mixture of all lights. Mixture of all lights in the visible region. In the visible region. May I ask you, what are all the possible lights in the visible region and how they vary according to their energies? How do they vary according to their energies, and what are all the possible lights in the visible region? If you know, can I define them with the Vibgyor thing? Vibgyor, violet, indigo, blue, green, yellow, orange, red. If you are going from here to here, your energy is decreasing, your lambda is increasing. That means the wavelength of red is highest, the wavelength of violet is the lowest, energy of violet is highest. I can say simply like that. Yes. So what someone did, what they have done is, they have taken a particle or a solution, okay, in which, of course, if this is a solution of something, electrons will be there. Of course, electrons will be there. They might have taken a combination of some atoms. Okay, what happens is, they have thrown some light onto it, which is a white light, which is a white light. White light has a continuous spectrum. What does white light has? A continuous spectrum. Okay, continuous spectrum means that all colors you will be seeing in it. If you are seeing the spectrum of a white light, what do you know? What do you mean by a spectrum of light? Let me show you quickly. Wait, just give me a moment. Just a minute, please. Just a minute, it is getting uploaded. I want to show you that. Have you seen this image before?
Yes,
No,
sir.
sir.
Someone said no, someone said yes. Okay. See now. Yes. See now. This is a image of spectrum of light. This continuous spectrum which I have written over here, na? Which color will work? Okay, let's say this. This one. This is nothing but your white light only. Having a continuous spectrum. This is a continuous spectrum, ranging, having all the possible colors here. Is it okay? Now, we know that one thing, that electrons can absorb some particular light energies. Which one? Which will be which will be equal to the delta E energy gap between the two orbits, right? So now you can see. Can you see this absorption spectra? Absorption spectra. What we have done on a particular atom, we have shined the whole white light, the whole visible region of light. Now, what happened is, whatever the light, okay, I will say this way. You have transferred the light, you have thrown the light, you have incidented the light on a particular atom or something, and then what happened is, some light maybe can be absorbed by the electrons, and the remaining light was collected. This is called the transmitted light. The light which is coming outside is called a transmitted light, and the transmitted light was collected, and the spectrum of that transmitted light was again recorded. Okay, we got this spectrum, this one. Can you see the spectrum? There are few lines, few missing lines. Can you see these lines? These particular light wavelengths or frequencies or the energies has been absorbed by the electrons to move their orbit from the lower orbit to the higher orbit, or from their to go from their lower orbit state to the higher orbit state. That is what happened. Okay, from a otherwise continuous spectrum, when we throw that whole continuous spectrum onto a atom, the electrons present inside that atom has absorbed few wavelengths of light, which are these. So you got black spots in between. We got some black spots in between. This is a black spot. This is a black spot, black spot, black spot. Why a black spot appears? Because these radiations are now missing out of the whole continuous spectrum. Why are they missing? Because these radiations has been absorbed by the electrons. And now, as I mentioned, that electrons are never stable. Electrons are never stable in their higher orbits. So they will come back. Yes, they will definitely come back. And when they are coming back to the lower orbits, they will again release the energy. See, if your electron is present at the higher energy state here, let's say my electron is here, and if he wants to come back here, how it is possible? If this electron is releasing some energy, yes, and that energy lies in the visible region again, and so you got this spectra. This is called the emission spectra. Your electron is getting emitted. Your electron is emitting the light in the visible region when it is coming from the higher states to the lower states. So see, whatever the radiations were absorbed by the electrons, the same radiations were emitted also by the electrons. I hope you can see it. This is called emission spectrum. Is it 100% clear to you guys? Please tell me. Is this clear?
Yes, sir.
Mrinal, you also?
Yes, sir.
Okay. So now I think that emission and absorption spectra is clear. This thing Bohr was able to explain 100% perfectly. 100% perfectly. This was the theory of Bohr. That okay, my electron is getting electron is taking the light, electron is absorbing the light, it is going to the higher excited state, which is possible according to its theory also, right? There are multiple orbits in which electron can jump if that energy difference matches with the light energy, right? Which is happening over here as well. But then something happened. Something more happened. Someone comes, Zeeman and Stark. Specifically, if I mention, it's not the part of AB syllabus again, I'm saying, but I want to clear this statement that Zeeman and Stark, they were two scientists, they came and they did the same experiment in the presence of magnetic and electric fields. Same experiments they have again repeated in the presence of magnetic and electric fields. What they saw is that whatever the emission spectra we are seeing here, na, that is further, wait, that is further having a very, 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 very small deviations, or like this, a very, very small, like this particular emission spectra also has multiple lines, not a single line. It is very, very thin, maybe more than 10 lines can be seen in that one line only. I'm saying in this one line, in this one emission line only, I am saying that this is also splitted into multiple lines. In the presence of electric field as well, in the presence of magnetic field as well, this was happening. And Bohr was not able to explain why this splitting of, these are called spectral lines, why the splitting of spectral lines takes place in the presence of magnetic field and the electric field. So this was the limitation of Bohr. In the presence of magnetic and electric field, spectral lines split. This was the limitation of Bohr which he was not able to discuss. This is the first thing, the first limitation of Bohr. Okay, I'm writing here limitations of Bohr theory. See, they from Bohr theory, they will ask you the concept only. They will never ask you any numericals. They will ask you numericals from the photoelectric effect or the graphs from the photoelectric effect. Okay? Or they will ask you the questions based on this topic. E is equal to hc by lambda, the Planck's theory basically. They will ask you numericals from here. Okay, I hope this is clear. Then this was the first limitation. And the new limitation which arises suddenly, you know what was that? There were in the emission spectra, see, only these lines are missing, na? From the absorption spectra, this line was missing, this line was missing, this line was missing, which are coming in the emission spectra of this electrons, right? But suddenly what happened? We have got even more, even more, you can say, disturbed emission spectra. We got multiple lines in the emission spectra which were not present, which were not absent in the absorption spectra as well. We got those lines as well. Maybe we got this line, so we got here as well a line. We got a line here as well. We got a line maybe here as well. Some more lines were appeared which were not appearing in the, which were not missing in the absorption spectra. Those lines were also appearing in the emission spectra. So then something again was missing from the Bohr side. Yes, there were many things which were missing from the Bohr side. This was again one of those things. Okay. So this also is not the part of our syllabus, but I'm just telling you that yes, these were few limitations that were, that is why the Bohr model was also not that is not that considered as a good model to understand this. Then sir, which type of model is being considered? I will tell you, after Bohr, there was no scientist who was discussing the about the particle nature of the electron. I am telling you right now, after Bohr, there was no scientist who discussed the particle nature of the electron. Everyone stopped discussing about the particle nature of electron, and because they now know that light can exist in the form of dual nature, it might be possible that our matter can also exist in the form of both particle and wave nature, dual nature. That matter can also have this thing. Matter means the electrons, the atoms, everyone, all the matter can have the particle and wave nature both. Yes. So the new research continues with the wave nature of light, which I will be discussing in the next class. I hope you enjoyed this class, right? It's fine.
Yes, sir.
So will you be able to do the questions if I give you regarding this topic, E is equal to hc by lambda and all? They are coming in the FRQ section. They are not asking you this thing in the MCQ section. That also I will tell you. The photoelectric effect is never asked in FRQ section. It is only asked in the MCQ section. Okay. So we'll be sharing you few questions. Please try to complete it. I will be sharing it by either today's end or tomorrow's end. Okay. We'll try to upload it. Okay. On the Google Drive. Mrinal, you are also doing the homework?
Yes, sir.
Okay. Are you able to complete it? No
Yes, sir.
issues?
Yes, sir.
Okay then. Okay then we will meet later. Okay. On Friday. Maybe it's possible that I will be changing the timings on Friday. I am not too sure right now. Maybe it's from 9 to 10. I will inform you on Thursday. Is it
Okay,
okay?
sir.
Okay.
Okay, sir.
Thank you. Bye bye. You can go.